Good afternoon. So I'll talk about dehazing. The weather prediction for today was that it would be gray and rainy, and I hope that that would be indeed the case, so that I'll have a strong motivation for my work. But apparently it was a nice day today, and but there are days where we take pictures and that's how they look, very hazy. Hazy images suffer from lack of contrast. It's hard to see the distant regions, and the idea of dehazing an image is estimating the haze and removing the haze from the image. Single image dehazing does that based on a single image. So first of all, we need the image formation model based on which we'll work. The formation model of image dehazing typically follows from the radiative transport equation that tells us how light propagates in space. I won't really go into the details, but the assumptions are that the changes of the light intensity are due to scattering. So light gets scattered by the rain droplets or dust, and then the scattered light is added from different directions. By integrating this equation along the lines of sight from the camera to the object, we get this relatively simple equation where basically the input image is explained to be as a convex combination between the haze-free image, J, and some constant color, which we call the atmospheric light vector, which is just the average color of the light that's undergone light scattering due to the haze. This is basically the whiteness of the haze or the bluishness of the haze. The scalar T and 1 minus T, so T is the transmission. It's the amount of visibility that can change at each pixel in the image. Both I and J and A are three-dimensional vectors in case of RGB images, and T is a scalar between 0 and 1. It's given by this term here. So this equation is ill-posed for the following reason. Even if we assume that we know these three constants, these three coefficients of the air-light vector, at each pixel we have three constraints, which are the input image, the red, green, and blue of the input image, I of x. Yet we don't know the four unknowns at each pixel, which are the three unknowns in J, the RGB of the output image, plus the scalar, the transmission, which is the scalar at each pixel. So altogether, we have one unknown that is basically impossible to determine based on a single pixel. So as I said, this is without counting the unknowns in A. And in this work, we will assume that we know the air light color, the atmospheric light vector color. This pixel per pixel ambiguity, it does have an analytic expression. Nevertheless, it's easy to explain it. It can be explained more intuitively that when we see a red pixel, we don't really know whether it was a very saturated red that was masked by a very thick layer of haze, or whether it is actually the color of the surface and there's barely haze between us and the pixel. So there's this one-dimensional ambiguity, the amount of haze, and the color correction that yield the same result. So this is the very reason why many previous work assume that they have more information about the scene than the image itself. So some images used more than one image of that same scene, taken under different weather conditions. Other methods by Yoav Shechner assume that the scene was taken under different polarization angles, which change the effect, the amount of haze, and therefore it can be subtracted. And other methods assume that they know the three-dimensional geometry of the scene, so when the depth is known, the transmission can be estimated based on this simple assumption. Single image dehazing methods appeared lately. Indeed, I presented one here 5 years ago, I think. Let me briefly talk about these three works. So the visibility in bad weather from a single image by Tan from 2008 solves this ambiguity by just searching for the output image that would be the most contrasty, right? The haze images suffer from low contrast, so let's search for one that has lots of contrast. So this is an input image, here's the output image, and this is the tour, the reference image for that scene. And we can see that the output image has the edges somewhat exaggerated just because it was maximized the derivatives of the image was maximized. So it gives nice solutions, but they are not entirely realistic. The single image haze removal of et al. Assumes that every channel, either the red, green, or blue of an image, vanishes at some point, at least in some neighborhood of every pixel. So if this is the case, the transmission can be actually estimated by this very simple term. And that assumption is not entirely correct at bright regions, where neither the red, green, or blue color channels vanish. And indeed, we see here a very severe error in the transmission. So this is high transmission. These people are close to us. But this object, which is closer to them, appears to have the lowest, probably the lowest transmission in the scene, which we know is wrong. Nevertheless, the image does look pretty good. And that's some good property of that method, that most of the errors that it does don't really appear that bad to us. It just removes too much whiteness from the stones here, and they appear over-contrasty, but we typically enjoy that. Nevertheless, if we need the transmission for some application, then the transmission map are fairly inaccurate in this method. The method I presented a few years ago, let me remind you what it consisted of. So the idea was to further separate the output image into shading and albedo components. And then by some algebraic manipulation, it can be shown that the ambiguity basically in the problem can be reduced to a single number that neighborhood of pixels share. So it's one scalar that can be estimated based on on a number of pixels around it. And the way to estimate this ambiguous number is the way it was proposed is to decorrelate the transmission from the shading. So wrong values of eta here cause the transmission and the shading functions to blend. And in order to estimate the right eta, the idea was to assume a lack of correlation between the shading and transmission functions. That was a canonical example that I used to show, that even in this particular point in the image where this function kind of depends on the event between the armchair, the arm of the armchair and the back seat. So both the shading changes there abruptly and the transmission change. Nevertheless, they're not strongly tied together. They don't have a linear relation between the two of them. Therefore, a lack of linear relation between the two can be offer us the solution. So the problems with this method is that it's quite sensitive to variations in R. It assumes that R, the albedo of the surfaces, is constant. It has no way of verifying that this is indeed the case. It has very severe SNR restrictions. And so it tends to overcorrect regions or undercorrect other regions. So it's not as accurate as the, for example, the dark channel method. But what all these methods share is that they make some assumption and they just follow them across the entire image, whether they're right or wrong. They don't have the ability to validate their assumptions across the image. And that would be the property that the new method achieves. I think that the striking property that I should have probably deduced 5 years ago when I saw these graphs in front of me wasn't that these two functions lack linear correlation, but that this function is actually very simple and it's piecewise constant. So if you do this, run this very simple statistic, you realize that if you look at very small image patches, which are the patches I was working with, 7 by 7 pixels, is that in 72% of the patches in the image, the transmission does not change by more than 0%, and in 1% of the images, in 82% of the patches in the image, it doesn't change, it changes below 1%. So basically, we can assume that the transmission in many patches of the image is roughly constant. So the new method simply assumes that in small patches of the image, the transmission is held constant. This is not the case in every patch in the image, obviously, due to depth discontinuities and so on. But let's assume that many patches do obey it. Actually, this is not a very surprising finding. People have studied the statistics of range images, of depth images, and so very similar behavior. We'll follow the assumption that previous method used, which is the fact that the albedo of the surfaces is constant in many patches. Nevertheless, unlike previous method, the new method will have the ability to verify this assumption as well. Given these two assumptions that T of x is T and R of x is R, we get, and we plug in these assumptions into the image formation model, we get this very simple explanation of small image patches in the image. So the input image patch, some small neighborhood, is what's basically changing there is just the shading coefficient. So it's the shading that is multiplying the albedo vector plus some offset vector in the direction of the atmospheric light and at the amount 1 minus the transmission. So basically, if we look at small windows, we look at the histogram of pixels, RGB pixels, we're expecting to see a line, and that line is offsetted from the origin by this term 1 minus t times the atmospheric light vector. So let me say here, mention here that Ido Omer and Mike Verman pointed out that in non-hazy images, small regions in images, in fact entire images in some cases, show color lines. The pixel distribution is restricted to lines. And they noted that in non-hazy images, these lines do pass the origin, which agrees with this observation that in case of hazy images, there is some offset, and the offset is proportional to 1 minus the transmission. Let me also mention another work with Mike and the students, Matan Sulami and Itamar Geltzer, where we've estimated the the atmospheric light vector, which is an important vector that one needs before starting to estimate the transmission, Dehazing image, which we presented at ICCP. So that work relies also on these two assumptions. Okay, so assuming this is indeed the case, and assume that we manage to extract patches in the image in which these assumptions hold, meaning that the pixels lie on a color line, the way we estimate the transmission is simply by evaluating the offset of that line from the origin. So we know that the offset from the origin is 1 minus the transmission times A, so we intersect the line SA, the line that is parameterized by the parameter S, and the color line LD plus V, and the intersecting those two lines basically requires us to solve this 2x2 system of linear equations, and when we get S, we can extract T as 1 minus S according to this law here. So it's as simple as that. So once I know the offset of the color line from the origin, I basically know the amount of transmission in that patch. So an overview of the algorithm, the idea is to scan the image, consider non-overlapping patches, and in a second iteration, even overlapping pattern, array of patches. And then at each of these patches, the idea is to estimate the color line and see that it indeed obeys certain rules that the formation model assumes that should occur, and skip patches in which these assumptions do not hold. So that's the part where the new method can identify patches in which its assumptions basically don't hold. Either pixels don't lie on a color line, or that color line doesn't obey certain rules that I would list in a slide. And that would give partial estimation of the transmission, as you can see here. And then in the paper, I propose some edge-preserving interpolation scheme that is typically is dedicated for this procedure in order to complete the transmission map, as we see here, and dehaze the image based on this transmission map. So I won't really go into the fine details of how the color lines are estimated in each patch of the image, but the basic idea is to run some ransack algorithm where you randomly sample 2 pixels from that patch. You define the line that these 2 pixels define as the candidate line, and then you check that line against a list of criteria which the model tells us should be the case. So one thing is that that would indeed be a line, that there are enough supporting pixels. That the direction of that line would be positive. As I noted, the direction of the color line should be the reflectance coefficients, and we know that the reflectance coefficients are all positive numbers, 3 positive numbers. We want a large intersection angle between the lines that we're intersecting. Otherwise, we won't be able to really believe the intersection point that we get. Unimodality is also required in the distributions of the pixels because edges do appear like two clusters of pixels that define a line. We don't want these cases. In these cases, we're not expected to get a constant transmission, so we detect that as well. And of course, low intersection error, we're intersecting two lines in R3, so they don't have to intersect. There is a distance between the two, so some threshold on that is also expected. And also, we expect the transmission value to be between 0 and 1. It's another criteria that we can check whether the solution gives that. And some more, let me just skip. And we repeat this several times, as we typically do with Ransack iterations. And if no line passes all these criteria, we just skip that patch and move on. And these are the patches where we need to interpolate the solution. But at least we know that we're not doing wrong estimations of the transmission, which is, I think, a better option, and so will the results show. So here are a few examples of patches. So this patch was rejected because there was a low angle between the two lines that were intersecting. Basically, the pixels here are all saturated with a haze. There's no way to distinguish between the content of the image and the haze. This is an example of a patch in which we have an edge, right, which we have these two clusters of pixels that define a line. And in this patch, the transmission is not constant. Our formation model is incorrect. This patch corresponds to some glossy surface, which is highly non-diffusive. So we get a large intersection error. In the red line, we see the difference in 3D between the lines that we're intersecting. Here is a case of a very constant patch. So we have low variability. We're tailoring basically a line through this bunch of points. We can't really assume that this is a reliable line. These are two successful cases. This is a case where the color line extracted does not pass through the origin, meaning that there is haze. This is a patch in which the color line does pass through the origin, meaning that there is no haze in that patch. So the main point is that the new method, based on this long list of criteria, can identify cases in which the assumptions do not hold and skip these patches. I think this is the main point of that method. So as I mentioned, given an input image, we have this partial estimation of the transmission in the image. We then interpolate it in some edge-preserving method, which is dedicated to this problem. And I urge you to look at the paper for details. And then we use that map in order to dehaze the image. So let's go to the results. Well, it's typically very hard to see the results of my works on LCDs, on projectors, but I think it should be possible. Well, it's impossible. So I think that there's a much more balanced reduction of the haze in this output image next to the previous one, which overcorrected up here, undercorrected here. I'm not sure how much you can see. The method of Hay et al. Has the tendency of overcorrecting, but then they add some undercorrection step in order to compensate for that. So altogether, they don't remove as much haze as they should be. Another comparison, here we see the method of Tan that maximizes the derivative in the image. So it makes an image which is very detailed in one sense, but not that realistic. So if you look closely, you can see quite a good Staten Island in our output image, which can't be seen in any of the competing images. Another two images in which I compare to the dark channel method of Hay et al. Once again, there's stronger reduction of haze in the in this proposed method. Some more images. This image I got from some of the plane pilots just across the road here of Herzliya, I think, Marina. Some quantitative results. So here we have two tests. The first test is a synthetic test where I randomly sample squares and randomly sample the transmission, and I know the ground truth, and I can compare the two. And in this case, I made sure that one of the RGB channels would indeed vanish, so that the assumptions of et al., the dark channel method, would be met. Nevertheless, the accuracy was higher by our method. In this test, both the estimation of the transmission and the output image. Another nice test that I tried here is to take an image which does not contain any haze and make sure that the method actually does not do anything to that image, which is not a trivial thing. So in this image, the pizza and the fruit image, we get a higher accuracy. So in general, a database of images where we have haze and we want to remove that haze, these are the comparisons. And in most of the cases, our method is superior to the method, my previous method, and the dark channel method. Although I should say that in case of high degree of noise, the method of et al. Becomes more accurate. And in fact, it offers a more accurate image estimation and lower accuracy of the transmission. Nevertheless, it's, the final output is more accurate in case of the dark channel method. So let me conclude the talk. Presented a new single image algorithm for estimating the transmission from a single image based on the offsets of the color lines from the origin in RGB space. This method is able to validate its assumptions across the image and avoid consistent errors, such as underestimation of the transmission, such as in case of the color channel method. The method is fairly fast. It takes less than half a second to estimate the transmission and solve the MRF using 5 seconds, or it's possible to replace that by a faster component for edge-preserving interpolation. So it takes basically a total of 0.55 of a second in order to dehaze an image, a 1 megapixel image on a 2.6 gigahertz computer, which are fairly comparable running times to the method of the dark channel method of et al. And also, as I said, there is a description of some dedicated MRF interpolation for the transmission that I explained in the paper, and I again refer you to the paper. So that should be it. Thank you.